Somewhere above the clouds of the largest planet in our solar system, a spacecraft the size of a basketball court is falling through a storm of radiation so intense that it would kill an unprotected human in minutes. It is not falling by accident. It has been falling on purpose, again and again, for almost a decade, threading a needle between the most violent magnetic fields in the solar system, just to send back a handful of images and a stream of numbers. And in the last few months, those numbers have told scientists something that does not fit the Jupiter they thought they understood. The planet is not simply bigger than Earth. It is not simply stormier, colder, or more violent. According to newly released data from NASA's Juno mission, Jupiter has been quietly rewriting 3 separate rules of physics at once, and nobody saw it coming until the raw images and raw measurements started lining up in ways that made veteran scientists stop and look twice. This is not a planet behaving the way a gas giant is supposed to behave. This is a planet where lightning is behaving like nothing seen anywhere else in the solar system, where invisible particles are being flung toward the speed of light in a region of space that should not be capable of doing that, and where the very shape of the planet itself, its physical geometry, the thing scientists thought they had measured to near perfection decades ago, has just been quietly corrected. 3 discoveries, 1 spacecraft, and a growing sense inside NASA's Jet Propulsion Laboratory that Jupiter has been hiding a more extreme version of itself in plain sight the entire time. For years, the public image of Jupiter has been frozen in a kind of postcard stillness. The swirling orange and cream bands, the great red spot, a storm larger than Earth that has raged for centuries. A planet that looks, from a distance, almost peaceful, like a marble suspended in the dark. But peaceful is the wrong word, and it always has been. What NASA's Juno spacecraft has been recording since it slipped into orbit around Jupiter is a planet whose interior and atmosphere are locked in a state of violence that dwarfs anything Earth's weather systems could produce. And the newest findings suggest that violence extends further and stranger than even the scientists running the mission expected. Start with the lightning, because the lightning is where this story begins to feel less like a science briefing and more like a warning. Earth has lightning. Humans have lived alongside it for as long as there have been humans, and there is nothing mysterious about it anymore. A buildup of electric charge in storm clouds, a violent discharge, a flash, and a boom. Jupiter has lightning too, and for a long time scientists assumed it worked more or less the same way, just scaled up to match a bigger planet. Juno's newest data says that assumption may be wrong. Some of the electrical discharges detected in Jupiter's atmosphere appear to unleash energy up to 100 times more powerful than the most extreme lightning bolts ever recorded on Earth. 100 times. Not double, not 10 times. 100. That number alone should stop you. On Earth, a single lightning bolt can vaporize sand into glass, split ancient trees down to their roots, kill instantly, and briefly heat the surrounding air to temperatures hotter than the surface of the sun. Now imagine that violence multiplied 100-fold, occurring inside clouds of ammonia and water ice, deep within an atmosphere with no solid ground to absorb the shock, in a planet with more than 300 times the mass of Earth. Juno did not have to imagine it. Its instruments caught the signal directly. Radio bursts and optical flashes recorded as the spacecraft skimmed low over Jupiter's cloud tops during its closest passes. Data that scientists have spent months cross-checking specifically because the numbers seem too extreme to publish without triple confirmation. What makes this more than a curiosity is the question it raises about how such lightning could even form. On Earth, storm intensity is limited by the physics of our atmosphere, by gravity, by the availability of moisture, by the balance of temperature and pressure that determines how high a storm cloud can grow before it exhausts itself. Jupiter's atmosphere plays by different rules, deeper, colder, denser, layered with chemistries that do not exist in Earth's sky. Scientists studying the new lightning data are now asking whether Jupiter's storms are drawing power from something beneath the visible cloud deck, some deeper reservoir of energy that Earth's storms simply do not have access to. If that is true, then the lightning is not just bigger. It is evidence of an entirely different kind of storm engine operating inside the planet, one that current models were never built to explain. And that is only the first of the 3 discoveries. The second one takes us away from the swirling clouds and out into the empty space that surrounds Jupiter, a region most people never think about at all. Every planet with a magnetic field creates an invisible bubble around itself, a magnetosphere, a boundary where the planet's own magnetic field pushes back against the constant outward flood of charged particles streaming from the sun. Earth has one. It is what creates the auroras at our poles. Jupiter's magnetosphere is the largest structure in the solar system after the sun itself, so vast that if it were visible to the naked eye from Earth, it would appear larger in our sky than the full moon. And at the outer edge of that magnetosphere, where Jupiter's magnetic field first meets the onslaught of solar particles, there is a boundary called the bow shock, and just ahead of it, a churning unstable region called the foreshock. For more than a century, physicists have wondered where the universe's cosmic rays come from. those extraordinarily high-energy particles that strike Earth's atmosphere after crossing unimaginable distances, some of them carrying more energy than particles produced in the largest particle accelerators humans have ever built. The search for their origin has spanned supernova remnants, black holes, and the shockwaves of distant stellar explosions. Juno's newest measurements have added an unexpected candidate to that search, one sitting right in Earth's own cosmic backyard. As Juno passed through Jupiter's foreshock region, its instruments captured particles being accelerated to nearly the speed of light, right there in the turbulent space just outside Jupiter's magnetic boundary, not somewhere billions of light years away. Not inside a supernova, within the shadow of a planet in our own solar system. Scientists studying the data describe the foreshock as a kind of natural particle accelerator, a place where the tangled, shifting magnetic fields grab charged particles and fling them forward again and again, each pass adding a little more speed, a little more energy, until the particles are moving close enough to the speed of light to qualify as the same category of high-energy cosmic radiation that has puzzled astronomers since the discovery of cosmic rays more than 100 years ago. If Jupiter's own magnetic environment can do this on a smaller scale, then the physics behind some of the universe's most extreme particles might not require exotic, distant, unreachable objects to study. It might be happening quietly, right here, every time a planet's magnetic field meets the solar wind at the right angle in the right storm of turbulence. That possibility alone is reshaping how physicists think about where cosmic rays are born. And it means Jupiter is no longer just a planet to study. It is potentially a laboratory sitting in plain sight, one that has been running this experiment on itself for billions of years, while humanity only just learned to read the results. The third discovery is the strangest of all, not because it involves anything explosive or violent, but because it involves something scientists thought they already knew for certain: the shape of the planet itself. Jupiter is not a perfect sphere. No rotating planet is. The speed of its spin causes it to bulge at the equator and flatten slightly at the poles. And for decades, spacecraft flying past Jupiter measured that bulge, that flattening, that overall shape, with instruments considered precise enough to settle the question. Juno was built with an even more sensitive tool, a radio occultation experiment, in which the spacecraft beams a steady radio signal back toward Earth's deep space network as it passes behind the planet, and scientists study exactly how that signal bends and shifts as it grazes Jupiter's atmosphere on its way to Earth. What that experiment revealed was not a wild departure from prior measurements, but it was enough of a correction to matter enormously to anyone doing precision science involving Jupiter. The planet's true shape, according to Juno's newest occultation data, differs subtly but measurably from the models scientists had relied on for years. It sounds like the smallest of the three discoveries, almost anticlimactic, next to lightning 100 times stronger than Earth's, or particles accelerated near the edge of the speed of light. But its consequences reach far beyond Jupiter itself, because Jupiter's shape and size are used as a calibration standard, a reference point, for how astronomers interpret the sizes and structures of giant planets orbiting other stars entirely. Planets discovered by telescopes so far away that scientists cannot see them directly, only infer their properties by comparing the light they block as they pass in front of their host stars. If the reference point itself was slightly wrong, then everything measured against it, from Jupiter's own internal structure to the size estimates of thousands of gas giant exoplanets across the galaxy, needed to be revisited. Put those three findings together, and a different Jupiter starts to emerge from behind the postcard image. This is a planet whose storms may be tapping into a power source scientists do not fully understand. A planet whose magnetic environment is quietly performing the same kind of extreme particle acceleration, once thought to require supernovae or black holes, and a planet whose exact physical shape, thought to be settled decades ago, has just been recalibrated by a spacecraft that had to survive radiation belts intense enough to fry ordinary electronics simply to collect the data. None of this happened by accident, and none of it happened quickly. Juno arrived at Jupiter in 2016, entering an unusual, highly elliptical orbit specifically designed to dip close to the cloud tops during each pass, and then swing far out again, both to gather close-range data and to limit the spacecraft's exposure to Jupiter's punishing radiation belts, among the most intense in the solar system. Intense enough that engineers built the spacecraft's most sensitive electronics into a titanium vault just to keep them functioning long enough to finish the mission. Every image from JunoCam, every burst of radio data captured during an occultation, every signature of accelerated particles recorded in the foreshock, has come at the cost of repeatedly threading that radiation gauntlet, mission after mission extension, year after year, far longer than the spacecraft was originally designed to survive. That persistence is part of why these three discoveries are landing now, nearly a decade into the mission, rather than in Juno's earliest years. Some of this data required years of repeated passes to accumulate enough signal to be confident in the results. The lightning measurements needed multiple close approaches during different atmospheric conditions to rule out the possibility that early readings were flukes or instrument errors. The particle acceleration findings in the foreshock required careful comparison against known models of cosmic ray behavior elsewhere in the galaxy, work that involved teams well beyond the immediate Juno mission, cross-referencing decades of astrophysics research into where high-energy particles are thought to originate. And the shape correction required dozens of occultation passes, each one adding a sliver more precision, until the accumulated data finally diverged clearly enough from older models to be published with confidence. What is emerging from all of this is not a single dramatic headline, but a pattern. And patterns are often more unsettling than isolated events, because they suggest something systemic rather than something anomalous. Jupiter keeps turning out to be more extreme in more categories than the models predicted. Its storms exceed Earth's electrical violence by orders of magnitude. Its magnetic environment performs a kind of physics once reserved for the most extreme objects in the cosmos. Its very shape required correction after decades of confidence. If a planet this close, this thoroughly studied, this repeatedly visited by spacecraft since the 1970s, can still surprise scientists on 3 separate fronts within the same short window of time, it raises an uncomfortable question about how much of what we assume we know about the rest of the solar system, let alone the thousands of giant planets orbiting distant stars, is built on foundations that were simply never tested closely enough to notice they were slightly wrong. There's also a deeper current running underneath these findings, one that connects Jupiter's newly measured extremity to a much older mystery in physics. Cosmic rays were first detected in the early 20th century, and in the century since, physicists have built increasingly powerful instruments, ground-based detector arrays spanning entire deserts, satellites, underground observatories, buried beneath mountains and ice sheets, all searching for the source of the highest energy particles ever recorded striking Earth's atmosphere. Some of those particles arrive carrying energies that current human technology cannot come close to replicating, even in the largest accelerators ever built. The leading theories have always pointed outward, toward the wreckage of exploded stars, toward the violent edges of black holes, toward astrophysical engines so distant and so extreme that studying them directly has always been essentially impossible. Juno's discovery in Jupiter's foreshock does not overturn those theories, but it does something almost as significant. It shows that at least part of that same fundamental process, the acceleration of particles toward relativistic speeds through turbulent magnetic fields, can be observed close enough to study directly, in detail, using a spacecraft humans built and flew there themselves. That reframes Jupiter's role in solar system science entirely. It is no longer simply the largest planet, a gravitational anchor that shepherds asteroids and shields the inner solar system from some fraction of incoming comets. It is now also a working laboratory for one of astrophysics' oldest unsolved questions, sitting close enough that a single spacecraft could fly through the actual mechanism and record it happening in real time. Every future mission to any planet with a strong magnetic field, and every future study of exoplanets, which may possess similarly extreme magnetospheres, now carries an added layer of significance because of what Juno found, simply by being close enough and patient enough to notice. The lightning findings carry their own layer of unresolved tension. Scientists still do not have full agreement on where the extra power is coming from. Some researchers point to the sheer scale of Jupiter's atmosphere, arguing that with far more available moisture and far greater atmospheric depth than Earth, storms simply have more raw material to draw on before discharging. Others suspect something related to the composition of the clouds themselves, layers of ammonia, ice mixing with water in ways that could generate charge more efficiently than Earth's simpler water-based storm systems. And a smaller, more provocative group of researchers has raised the possibility that Jupiter's internal heat, the residual warmth left over from the planet's formation billions of years ago, which still radiates outward and makes Jupiter emit more energy than it receives from the sun, may be playing an active role in destabilizing the atmosphere from below, feeding energy into storms that then discharge with a violence Earth's atmosphere, powered only by sunlight, could never produce. No consensus has formed yet. What has formed is agreement that the old assumption, that Jovian lightning is simply an oversized version of Earth's, no longer holds up against the data. Meanwhile, the shape correction, quiet as it sounds, is already rippling outward into a completely different branch of astronomy. Telescopes searching for planets around other stars rely heavily on a technique called the transit method, watching for the tiny, precise dimming of a star's light as a planet passes in front of it. Calculating the size of that distant planet from the amount of dimming requires an extremely accurate reference model of a known gas giant, and for years, that reference has effectively been Jupiter. A correction to Jupiter's true shape, however small, means every model built on top of that reference needs to be checked, refined, and in some cases adjusted, a ripple effect touching thousands of exoplanet-size estimates collected over more than a decade of observations. Nobody is suggesting a catalog-wide crisis, but nobody is dismissing the correction as trivial either. And the scientists behind the finding have been explicit that this is exactly the kind of subtle recalibration that, multiplied across an entire field of astronomy, quietly changes conclusions that seemed settled. What ties all three threads together is not coincidence, but timing. Juno's mission has been extended repeatedly past its original end date, each extension approved specifically because the spacecraft kept surviving longer than engineers expected and kept returning data too valuable to walk away from. The mission was never designed to answer questions about cosmic ray origins or exoplanet calibration standards. It was designed to study Jupiter's interior, its magnetic field, its composition. But that is often how the deepest discoveries happen, not through instruments built to find something specific, but through instruments built to look closely enough, for long enough, that something unexpected eventually surfaces on its own. There is no dramatic collision looming, no threat to Earth, nothing in these findings that changes tomorrow's forecast or tomorrow's headlines outside the scientific community. But there is something quietly unsettling in the pattern itself. A planet visited by spacecraft since the 1970s, orbited continuously by a dedicated mission for nearly a decade, studied by some of the most capable instruments ever built, still had three fundamental surprises left to give, all surfacing within the same stretch of time, all forcing scientists to revise models that had stood for years or decades. If Jupiter, the most examined planet after Earth itself, still held secrets this fundamental, the obvious question extends outward to everything else, every other planet, every distant exoplanet, inferred rather than directly observed, every assumption built on data collected just once, just briefly, just well enough to seem sufficient at the time. There's a practical dimension to all of this as well, one that reaches beyond pure curiosity and into the engineering decisions being made right now for the next generation of missions. NASA and other space agencies are already designing spacecraft intended for Jupiter's icy moons, Europa, and beyond, worlds that orbit inside the same punishing radiation environment Juno has spent years fighting through. Every new data point about how violent Jupiter's magnetosphere actually is, how powerful its lightning can become, how energetic the particles swirling around it truly are, feeds directly into how those future spacecraft are shielded, how their instruments are calibrated, and how long engineers can realistically expect them to survive. A miscalculation based on outdated assumptions about Jupiter's environment is not an abstract academic risk. It is the difference between a mission that returns a full decade of data and one that goes silent within months, its electronics quietly destroyed by radiation nobody accounted for. In that sense, Juno's newest findings are not just rewriting textbooks. They are actively shaping the blueprints of missions that have not launched yet. There is also a quieter, more philosophical thread running through all of this, one that scientists rarely say out loud in press briefings, but that shows up again and again in the way they talk about Jupiter privately. For most of the 20th century, the outer solar system was treated as essentially finished business, a place mapped in broad strokes by the Pioneer and Voyager flybys, then filled in with detail by Galileo and now Juno, a process assumed to be converging toward a complete picture. What these three discoveries suggest instead is that convergence was an illusion built on the limits of earlier instruments, not on the actual complexity of the planet itself. Each generation of spacecraft has arrived carrying tools sensitive enough to expose the blind spots of the generation before it, and there is no particular reason to believe Juno represents the final word rather than simply the current one. If radio occultation experiments only now revealed a shape correction that decades of earlier flybys missed, if it took years of accumulated lightning data to reveal power levels 100 times beyond Earth's, if a foreshock acceleration mechanism this significant sat undetected until instruments sensitive enough finally passed directly through it, then the honest conclusion is not that Jupiter has finally been fully understood. It is that understanding a planet this size, this dynamic, this old, may simply take longer than any single mission, however extended, however successful, can deliver. That leaves scientists in an unusual position, publicly celebrating a series of genuine breakthroughs, while privately bracing for the likelihood that each one will eventually be revised again by whatever mission comes next, carrying whatever more sensitive instrument humans manage to build in the years ahead. Juno itself is not immune to that same fate. Its own measurements, however carefully verified, however many times cross-checked against archived data, exist within the limits of the technology available in the 2020s, and someone, someday, flying a more capable spacecraft through the same clouds and the same magnetic storms, may look back at these very findings the way today's scientists now look back at the older models Juno just corrected. Useful, honestly obtained, and ultimately incomplete. For now, the spacecraft keeps flying its long, looping orbit, diving toward the cloud tops every few weeks, gathering another slice of radio data, another set of lightning readings, another pass through the churning foreshock where particles get flung toward the speed of light. Each pass adds to an archive that NASA scientists openly admit they have not finished analyzing, an archive that may already contain signals nobody has looked at closely enough yet to recognize as significant. Jupiter has been sitting in roughly the same orbit for over 4.5 billion years, largely unchanged in its basic outline, since long before Earth had an atmosphere capable of supporting life. It is not Jupiter that has been changing, it is the resolution at which humans are finally capable of seeing it, and that resolution keeps sharpening year after year, mission after mission, in ways that keep exposing how much of what once looked settled was never as settled as it seemed. Juno continues to orbit, continues to dive close to the clouds and swing back out past the radiation belts, continues gathering data that will take scientists months or years to fully process. Somewhere in the backlog of measurements, still waiting for analysis, there may be a fourth discovery already sitting quietly in the numbers, waiting for someone to notice the pattern. Whether it will confirm what has already been found or overturn it entirely is a question nobody at NASA is prepared to answer yet. What they will say, cautiously, carefully, in the language scientists use when they know they are standing on the edge of something they do not fully understand, is that Jupiter is not finished surprising them. And after what the last several months have revealed, very few of them are willing to guess what comes next.